For our project, we'll be focusing only on one projection, Epsg 3857. So let's take a look at that now. Epsg 3857 is sometimes known as web Mercator, spherical Mercator, or pseudo Mercator. Now we've met the Mercator projection before. It was the map that we talked about distortion with. And given that these names all have Mercator in them, and one of them mentions pseudo Mercator, we know that this projection is going to be very similar to the Mercator projection. The actual difference between Epsg 3857 and a true Mercator projection is that Epsg 3857 approximates the Earth as a sphere. That's where the word spherical comes in spherical Mercator. The Earth is actually what's known as an oblate spheroid. Basically, a sphere that's been squashed a little bit. This has implications on how the projection renders the map. But generally speaking, for the area we're looking at, which is most of the landmass between the poles, the projections are pretty similar. Epsg 3857 is also known by another numeric code, Epsg 900913. This code was created by Google, as was the projection originally. Notice how the number 900913 somewhat resembles the written word Google. Both 3857 and 900913 refer to the exact same projection, and open layers can use either one. It really only becomes an issue when you're requesting data from a third party. A lot of times when you're requesting data from other sources, you need to let the source know what projection you would like to use. And the projections that they recognize may differ. Some may use 900913, some may use 3857. If you look in the Epsg Online catalog, you won't find an entry for 900913, even though it's often written with the Epsg prefix. You may come to find that Epsg is used by many as a proxy label for the word projection, even when the projection in question isn't officially recognized in the Epsg dataset. So let's take a quick look at the Epsg registry and code 3857. You go to retrieve by code and you can punch in the code that you want there and retrieve. Notice that there are two results here. The type that we want is a projected CRS, projected coordinate reference system, and therefore we'll pick this top entry. Here we go. So you can see here on the right in the remarks section, it mentions the fact that this uses a spherical development of ellipsoidal coordinates, and that there's a small error introduced with that. It also talks about the scope, that certain web mapping and visualization applications are using it. Incidentally, it's also mentioning that this is not a recognized geodetic system. A geodetic system is basically just the way that the Earth is represented in the projection. As I mentioned, in this case, the Earth is approximated as a sphere, whereas it's really an oblate spheroid. If you want to know more about the geodetic system that a projection is based on, you can just click on the base geodetic section. In this case, it uses the WGS 84 geodetic system. WGS simply stands for World Geodetic System. 84 is the year that this was created. Items included in the geodetic system are things such as the radius of the Earth, the exact center location of the Earth, things like that. Since projections are just mathematical translations of points on the globe to points on a map, you can convert data from one projection to another. The math behind exactly how this is accomplished is beyond the scope of this course, but as we'll see, OpenLayers does have the built-in ability to do this for a limited set of projections. And that capability can be expanded to work with many different projections by combining OpenLayers with another open source project called Proj4. We're not going to go into Proj4 in this course, but you can check it out for yourself at its home on GitHub, github.com/osgo/proj.4. In a nutshell, Proj4 is just a large library full of transforms between every different projection that you could think of. OpenLayers also allows you to write your own transfer functions if you want to go that route. So now we know the general idea behind how maps are created. A scale is chosen, which will determine the overall size of the map, and a projection is chosen to determine the location of all the items on the map. So that's all good. But how do we specify the regions on Earth that will then feed into the projection to get the locations on the map? For example, if we wanted to locate Slapout, Oklahoma on a map, how would we do that? So here we have a map of the US, and the pin represents the location of Slapout, Oklahoma. So you could say that Slapout is located just a bit north of the corner of the Oklahoma Panhandle, but that's not very precise. How far is just a bit north? Even worse, what happens if you need to locate Slapout, Oklahoma on this map? We need a way to refer to a point's location using fixed reference points, both on the Earth and on our map. In other words, we need coordinates. The position of any point on Earth can be defined by its latitude and longitude. Latitude and longitude are angles and are measured in degrees. Latitude is the number of degrees north or south of the equator, and longitude is the number of degrees east or west of the prime meridian, which runs from the North Pole down through Greenwich, London, West Africa, all the way down to the South Pole. The combination of a point's latitude and longitude are known as its coordinates. So for example, the coordinates of the White House are approximately 38.9 north and 77 west. Sometimes you'll see latitude and longitude expressed as positive and negative numbers. A negative value simply means south for latitude and west for longitude. And to answer our question from the last slide, Slapout, Oklahoma is located at 36.6156 degrees north and 100.1081 degrees west. So how do we translate those coordinates on Earth to a point on the map? We simply feed them into the mathematical model that is our projection. What comes out is an x and y value that we can then plot on a two-dimensional coordinate system. And in case you slept through geometry as well as geography, a two-dimensional coordinate system looks something like this. So we simply take the coordinates of the point on the globe that you want to plot on your map, pass it into the projection, and out comes an x and y value which you can then plot on your map. So let's recap what we learned in this module. Scale is the ratio of the distance on a map to the physical distance on the Earth. Scales are unit agnostic. A scale of 1 to 10 can be read as 1 inch on the map equals 10 inches on the Earth, or 1 meter on the map equals 10 meters on the Earth, or any other length unit you want to use. A projection is a mathematical method for converting locations on the Earth to locations on the map. Many projections are cataloged by the Epsg and are referred to by the numeric identifier, such as Epsg 3857, which is also known unofficially as Epsg 900913. Incidentally, latitude and longitude are referred to as Epsg 4326, even though a map using latitude and longitude directly as values of x and y is said to be unprojected. That is, there was no projection performed to convert the latitude and longitude to x and y values. A location on the Earth can be described in terms of its latitude and longitude, where latitude is the angle north or south of the equator, and longitude is the angle east or west of the prime meridian. A projection is used to convert that latitude and longitude to the map's Cartesian or two-dimensional coordinate system. So why did we just go through all that? Well, one of the key features of OpenLayers is that it allows you to use data from many different sources. And those different sources will often use different projections. So you need to understand a little bit on how to work with different projections so that things all line up nicely on your map. And you'll also need to understand scale in order to understand how OpenLayer's zoom levels work. And more specifically, to understand how to limit the visibility of features at different zoom levels. And now that you got that under your belt, we're going to take a second to look at where to find free data for your maps.